Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, apply operations to make two strings equal. The problem is very interesting and can be solved in various different ways. You can apply some observation beforehand and can reduce the problem to a very simple dynamic programming problem. Or if you don't want to apply any kind of observation beforehand, you can solve this problem with simulation as well, starting from the brute force solution. So in this particular video, I will be focusing on the second variation of the solution, in which we'll not make any observation in front, and we'll start from brute force and try to optimize the brute force solution step by step. The major reason of covering that particular solution is to show you that how general it can be applied in other kind of problems as well. I would link two or three problems in the description below, which can be solved in almost a similar technique. So if you are new to this technique, after watching this video, you can solve those three problems by yourself or watch the video to just get a better understanding of this particular technique. So with that, let's get started. The problem states that you are given two zero indexed binary string s1 and s2 and a positive integer x. You can perform the following operation any number of times. The operation is you will choose two indexes I and j and flip s1i and s1j. The cost of this operation is x, right? Or you will choose an index I and flip s1i and s1i plus 1, and the cost of this particular operation is 1, right? So either you choose any two indexes and flip them, and the cost of that particular operation is 1, or you choose adjacent indexes and flip them, and the cost of this particular operation is 1. So you can do this operation any number of times, and your task is to make the string s1 and s2 equal, and you need to return the minimum cost needed to do so. If it is not possible to make them equal, we have to return -1. So let's take an example. Let's say s1 is this and s2 is this and x is 2. Basically it means we have to make this particular s1 string equals to s2 by making some modification to this s1 string, and the modifications allowed are we can flip two adjacent characters with a cost of 1, or we can choose any two index, flip both the indexes with a cost of 2. So let's see, if we apply the second operation, basically flip the adjacent indexes starting from index 3. If you flip these two indexes, you can see these two indexes initially was 0 0. If you flip them, it will become 1 1. So after one operation, this is the state. Now again you choose I equals to 4 and apply the second operation again. Basically you flip the adjacent indexes, so this one will become 0 and this one will also become 0. So this is the state after two operation. Notice that both the operation will cost you 1 because they are the operation of second kind. Now finally we can take the first index and the second last index and apply the first operation here, and this will incur a cost of 2. So after this operation, you can see this string is exactly equals to the original string s2, and hence we are able to convert this s1 to s2 in 3 operations. The first operation with a cost of 1, second operation with a cost of 1, and third operation with a cost of 2. So in just 4 cost we are able to convert this. You can try out any other possible combination. You will not be able to get s2 from s1 in less than 4 cost, and hence the answer here is 4. So hope the problem statement is clear. Now how to solve this? So let's say this is our s1 and s2. We need to make them equal. So let's start focusing on the first character only. So we need to make s1 and s2 equal. It means that we need to make this 1 2 0 for sure. In other words, we need to swap, or we need to flip this particular index for sure, no matter what. So there are two choices, right? Either you will flip it with the immediate next character, right? Or you can flip it with any other index, right? The first thing where you are flipping it with the immediate next character, this will incur you a cost of 1, right? The second piece where you are flipping it with any of the other indexes, that will incur you a cost of x, right? So let's say you flipped it. Let's assume that you flipped it with the adjacent character for now, right? If you flip it with the adjacent character, this will become 0, right? And this will become 1. So now what you need to know, you need to now figure out what is the minimum cost in which I can make this remaining string starting from index 1 equals to the string s2 starting from index 1. Isn't this problem exactly equals to the original problem? Original problem was give me the minimum cost in which I can make these two string equal. Now the reduced problem is give me the minimum cost in which I can make uh, some reduced string equal. So hope you can see the recursion here, right? So let's see the recursion in action. So initially this is our s1 string 1011110, right? Now we have to reverse this string for sure, like, because we know that we need to match it with the first character of s2. So we have to reverse this. So there are two choices: either you will reverse it with the immediate next character, and that will incur you a cost of 1, and if you flip it with the immediate next character, this will become 0 and this character will also be flipped, so it will become 1, right? Now second choice could be you can flip it with any other character, either this or this or this or any other one, right? So all of these will incur you a cost of x, right? Now if you do this particular flip, what will happen? This will become 0, right? So you can see this is now become 0. So this is the new string that you have. Similarly, if you flip it with this particular character, this will become 0, right? And you can see this is the case here, right? So once you reach these states from initial string, what you can simply do, this index is already taken care of. Now you want to know what is the minimum cost required to make this particular string equals to the remaining string and in s2, right? So what you can do, you can simply call the same function f. Let's say this is a function f which you have called with this particular string. So you can call this same function f with this string this time, right? Now whatever you will get from this function f, you will just simply do 1 plus that, and that is the cost if you take this path, right? In the same fashion, you will call the same function f for this particular string as well. Whatever you will get from this particular function f, x plus that will be the cost of this particular path. And in the same fashion, you will call this function for other indexes as well, and you will get the cost of all the paths. Now once you have cost of all the paths, you will simply do a minimum. You will take a minimum across all of these, and that will be your final answer, right? So hope this entire solution makes sense. Let's look at the pseudocode. The pseudocode is exactly what we have just discussed, right? So if you see this, what we will do, we have two things, index and s1. You can also take s1 as well, simply trim it, but I kept index so that it will keep track of from which index I need to make things equal, right? Now here, if this is like the base case and the memorization piece, so let's skip this for now. What we are doing, if the current character is equals to the character at s2, if that's the case, I don't need to make any changes, so they are already equal. For example, these two characters are already equal, right? And I don't need to make any change. So in this way, in that case, I will simply say give me the cost in which I can make this string after this equal, right? So I will simply call f of index plus 1 comma s1, which basically means give me the cost in which I can make everything after index plus 1 equal, right? If they are not equal, for example this 0th index itself, if they are not equal, there are two choices: either you will swap it with the next index, or you will flip it along with the one of the other index, right? So this is the piece where we are flipping it along with the next index. So you can see what we have done is we simply take this string, make a copy of it, and swap the adjacent indexes. So this jor1 is basically a fancy way of swapping 0 to 1 and 1 to 0. This is just a swapping. So we just swap the indexes, index and index plus 1. Now whatever s1 dash we get out of this, we'll simply call the same function f for that particular s1 dash. And this one is because we have swapped the adjacent characters or adjacent indexes, and hence we have incurred a cost of 1. Now the second case could be, you can swap it or flip it along with any of the other indexes. So anything starting from index plus 2 all the way up to n minus 1, you can swap it with any of the indexes, and for that we have done exactly same thing. We just swap the current index and the next index, and finally we call f for that s1 dash. This time we have added a cost of cost. Basically this is the x in the given problem statement, because swapping it with any other index incurs a cost of x, right? So after this we will get what is the minimum cost required to make the string after index equals to s2. This particular string equals to s2, right? Now what is the time complexity of the entire solution? The time complexity of any recursive solution with memoization, basically we are doing memoization as well, so that we don't end up computing the same state again and again, right? So time complexity of any recursive solution with memoization is simply the number of states multiplied by the complexity in each state, right? So what is the number of states here? Number of states is number of unique value of index, which is n, and number of unique value of s1. So s1 is a string, right? And the size of this string is n, and each position can either be 0 or 1, right? So in total there are n position, each can either be 0 and 1. So in total s1 can have, in worst case, 2 power n distinct values, right? So this is the number of state. Inside each of these state, what we are doing, in worst case we are doing a order n loop here, right? So this is the worst case thing that we are doing inside this particular loop. So this will be multiplied with order n. So this is the overall time complexity, n square into 2 power n, of this particular solution. So this will surely not pass the given time constraint, because n is up to 500, so 2 power n is very huge, right? So we have to optimize this, and you can clearly see if we are able to remove this 2 power n, our solution will be very, very efficient. So where from this 2 power n comes? This is coming from the s1, right? And why we need s1 in the state? We need s1 in the state because we are modifying s1 once here and second time here, right? So if we are somehow able to not modify s1, we can simply remove s1 from our state and keep it constant just like s2, because we are not modifying s1, then s1 is completely constant. We can simply say it is constant, we don't need it in the state, right? So we have to somehow remove this two modification of s1. In other words, what we want is, we still want to know that I need to flip a particular index, but I don't want to actually modify the index, right? So I would encourage you to pause and try to solve this first piece by yourself. Like, let's just try to remove the modification of s1 as a part of next index. So if you are pairing it with the next index, let's just try to modify let's just try to not modify s1 and still have this entire solution. So hope you have thought about it. The solution is very straightforward. Instead of actually modifying s1, we can simply take in a flag and maintain a flag which will denote whether whether the current index needs to be modified or not, right? So when we are actually, previously you can see we are doing s1 of index, right? But now we are not modifying s1, and this reverse next flag will denote whether to reverse the current index or not. So we have to check this flag. If this flag is true, it means I need to flip the current index. Otherwise, the current index would stay whatever it is currently, right? And once we have this value, we can simply do everything as it is. Now notice we don't need to modify s1 anywhere here, and we can simply, while computing the value of f, we can simply send a true here. Everywhere else it is false. This should be false here as well, sorry for that. So everywhere it is false, and simply here it will be true, which will denote that I will be modifying the next index, right? So this entire thing, remove the modification of s from here. Let's now try to modify, remove the modification of s from this particular loop as well. So again, I would encourage you to pause and try to think this by yourself as well. So what is happening here? We are pairing up this index with one of the index afterwards, and we are saying that this particular index will be reversed along with this index, right? Now we have discussed this multiple times in this channel. So whenever we are trying to pair up, we can see if this exact index is required in this particular iteration or not. If it is required in this particular iteration, we can't avoid this loop, right? But if it is not required in this particular iteration, we can skip this loop as well. So that's what we will be doing. In this particular case, we are modifying next, right? But we actually don't care which index this index is mapped to. So we actually don't care what exactly is the value of next to calculate any state of this f of index, right? So we'll defer that decision, and that's what will improve the time complexity as well. So let's look at it. So we maintain one more flag, which is reverse any. So what we are saying is, instead of finding out the exact index, I will just simply say that I need to reverse an index. No matter what index I will reverse, I have the power to reverse. That's exactly what we are saying, right? So based on that, what we will simply do, we'll simply make this flag true here, if it is not true. And if it is already true, it means I already have the power to reverse. So I will simply use that power instead of reversing it again. So let's just take one small example. Let's say you are trying to match 0 with something, right? Now you don't know which of these you will be matching 0 with. So you will simply say, okay, I will be matching 0 with something. And with this statement itself, I have a power of flipping one particular index without any cost. Because when we are saying that I will be mapping 0 with something afterwards, I already, let's say, incurred a cost of x. So now I have a power to actually reverse a particular index without incurring any cost. So instead of fixing the index, I will simply say I have this particular power, right? Now what I will do, whenever a index comes which need swapping, and if I am not swapping it with the adjacent index, and I decided to swap it with something else, let's say there is other indexes as well here, right? So I decide to swap it with something else. I will before swapping, I will first check this power thing that I have in my pocket. If I already have the power to reverse a index, instead of making a new pair, I will use this power and reverse this particular index without any cost, right? In other words, what we are saying is 0 is mapped with 5. This is just a fancy way of saying the same thing. Previously, we are mapping this, let's say index is 0, so we are mapping this index with 5 in this iteration itself. Now we are saying 0 with 0 that I have a power, and whenever 5 will come, I will use that power and map, and that will mean that 0 is mapped to that particular index, right? So that's what is happening here. We will have a flag reverse any. This flag will denote if I have a power to reverse any index. If I already have a power to reverse any index, and I will be reversing I need to reverse any index, I will use that power. If I don't have the power, I will create one mapping, and it means I will incur some cost here as well, right? So let's take one example that will make this entire thing much more clear. So let's see, let's say we have the exact same string s1 and s2 and we want to make them equal. So before jumping, like we know that this string needs, this particular position needs to be reversed. So first of all, we'll start with f00. The first 0 denote the index after which I need to reverse everything, and second 0 denote the whether I need to reverse this particular index or not, and third 0 denote whether I have a power to reverse any index or not, right? So currently it's 0, it means whatever is here is the correct value. I don't need to reverse this. So it is 1 and the s2 is 0. So one flip is required for sure, right? So we need to flip this particular index. So there are two choices again. If I can flip it with the next index, or I can flip it along with any other index. So if I flip it with the next index, what will happen? I will now need to answer that what is the cost to make the string after index 1 equal, given that index 1 is flipped, right? So that's what we have done. Index 1 is flipped, right? This was reverse next flag, and I need to find out what is the minimum cost required to make everything after index 1 equal, right? The second choice could be, and this will incur a cost of 1, right? Second choice could be, I will not use this adjacent matching. Instead, I will map it with something. What is something? I don't care. I just care that okay, I will be mapping it with something else, and that will incur me a cost of x. And because I am mapping it with something else, I also gain a power that I can reverse any of the index without incurring any cost. Because let's say I need to reverse this particular position, I can simply say if I have power, I can revert it, because it means 0 was mapped to 4, and because I have paid that cost already, I don't need to pay that cost again, right? So we'll go there. So basically, we now have a power that we can reverse this. We can reverse any string, and this will be the total. This will be the state that I need the answer for, right? Now let's talk about f110, right? What does this mean? This means that I need to figure out what is the minimum cost required to make everything after index 1 equal, given that index 1 is reversed, right? So even though it is 0, it is actually 1, right? Now because these two indexes are equal, I don't need to do anything, right? So I can simply say whatever, give me the minimum cost to make everything after 2 equal. So that's one possible state. Second thing what you can do, okay, you can say okay, I will reverse this, right? If you reverse this, you have to reverse this 2 times, right? So you reverse this with adjacent, and you reverse this with something else as well. So in that case, if you reverse this with adjacent, you have to reverse the next character, and you have reversed this with something else as well, because at the end you need the exact same value, so you have to flip it twice, right? If you reverse this with something else as well, you gained a power. But obviously this is not a smart move at all, because here you are incurring both the cost, and that is absolutely useless. So we'll not go in this path ever. This is just one possibility, that's why I just showed it, right? But now let's say we are trying to find out f101. What does it mean? It means I need to find out what is the minimum cost required to make everything after 1 equal, right? And this is 0. It means I don't need to reverse anything. So this was 0 and this will remain 0. Now this is 0 and this is 1. So I need to flip for sure, right? So two choices again. Either I will flip it with the next index, or I will flip it with some of the other indexes. If I flip it with the next index, I will be flipping it with 1, right? I will be incurring a cost of 1, and what I would want is give me the minimum cost required to make everything after index 2 equal, given that index 2 is reversed as well. So that's what we have done. Give me the cost to make everything after index 2 equal, given that index 2 is reversed, and I haven't used this power, so this power still remains with me, right? The second choice could be I will flip it with some other indexes, right? So now this is interesting. So you are saying that I will be flipping it with some other index. So instead of making a new pair, you will simply check if you already have a power in your pocket. If you already have a power, you can simply flip it without doing anything, right? Without incurring any extra cost, you can simply flip it, because this cost you have already have paid when you have made the first flip, right? So because you have a power, you can simply flip it and say what is the minimum cost required to make everything after 2 equal without the 2 getting flipped, right? This is what you need now. The same way, let's talk about the last state, this particular last state once last time. F211, it denotes give me the minimum cost required to make everything after string after index 2 equal, given that 2 is also reversed. So this is 1, it means that 2 is also reversed. So basically it is not 1, it is 0. Again they are different. 0 is not equals to 1, so we will reverse. Either we can flip it with the adjacent one, or we can flip it with something else, right? If you flip it with the adjacent one, what you need the minimum cost required to make everything after index 3 equal, given that 3 is also reversed, because you have reversed the adjacent ones. So that's what it is. Give me the minimum cost required to make everything after index 3 equal, given that 3 is reversed and I haven't used this power, so this power remains with me, right? And finally, if you map it with something else, again the same thing, you will check if you already have power. If you already have power, you will use that power instead of creating a new mapping, right? So you will simply say I will use this power, and because I am using the power, I will not incur any cost at all, and I simply need to figure out what is the minimum cost required to make everything after index 3 equal, right? So hope this entire dry run makes things clear. So let's look at finally the time complexity of this entire solution. The time complexity will simply again be the number of states multiplied by what we are doing inside each of the state. So number of states is now number of distinct value of index, which is n, number of distinct value of reverse next, which is 2, basically either true or false, number of distinct value of reverse any, which is again true or false. So this is the number of states. Inside each state we are not doing any looping and anything, so everything is just constant time operation. So we are doing some constant time operation inside each state. So overall complexity is just order n, which will like happily pass the given time constant. So if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself, because that's the point where you will understand which piece you haven't grasped. And as I mentioned in the beginning of the video, I would be linking some of the other almost similar problem in the description down below, so you can check them out and solve that as a fast follow. So next we'll be looking at the code. The code is exactly what we have discussed. We will simply call f of 0, 0, 0. Now inside this f, this is the base state. We'll cover that later, but inside this we'll simply figure out whether a flip is required or not. If a flip is required, if a flip is not required, I don't need to do anything. Basically I need to reverse the next string, next index, and whatever power I have will remain with me because I haven't used it at all. So this is what the value of answer would be if I don't need a flip. If I need a flip, there are two choices. Either I will flip with the next index. In that case, I will incur a cost of 1. And because I am flipping it with the next index, this particular argument would be 1, which means I need to flip the next index, and whatever power I had will remain with me because I haven't used this power at all. The second choice could be I can flip this index. I can use the power, and if I am using the power, I will be incurring some cost, and that cost, like I can either use the power if power exists. If power doesn't exist, then I can simply make a flip and say that I now have a power. So this var flip zor1 is just a way of saying if power exists, use it. If power doesn't exist, just start a new pair and incur some cost accordingly, right? So the base case is saying that if next flip is 0 and far flip is also 0. Basically, I should not have any extra power with me if I have exhausted all the string, and I should not be dependent on that the next string is actually reversed. So if both the cases are satisfied, then only will return 0. Basically, the whatever configuration we have made during the recursive function is correct. If that is not zero, if any of this is not true, it means whatever configurations we have made till now is not actually making the two string equal with the given operations. So hence we return something infinity. So we have to consider 110 to the power 9 as infinity. And finally, we'll just check if answer is infinity. If it is, we'll return -1 as the result. So hope this entire thing makes sense. If you have any doubts, feel free to follow up in the comment section below. I would be able to answer. Again, the main motive of showing this entire piece was to help you understand how you will like how doing small trick can help you optimize the recursive state, and you can use this technique in other problems as well. So if you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.